Welcome, class. I'm going to give you a quick little lesson here on lesson 2.3 and 2.4 in the book. 2.3 is on continuity, continuous functions. This should be a repeat of what you had in class last year, Intro to Calc. We talked a little bit about continuity. Feel free to pause the video if you feel like there's anything important to write down, and I'll kind of give you some of the highlights of very important things. Most of the things that we do in calculus will require that functions be continuous. So you have to know the function continuous to know if you can apply the calculus. This sentence right here, a function is continuous, if you can draw it in one motion without picking up your pencil, is not the proper definition, but it's a quick little definition you could always use. It is unacceptable to use that definition on the AP test. This is the thing you need on the AP test. A function is continuous at a certain spot or point if the limit is the same value as that of the function. So I'll give you an example. Right here, this function here is not continuous at this point in time because the limit approaches 1, yet the function is at 2. This is a continuous part of the function. This is a continuous part of the function. This is a continuous part of the function. This is not, because the limit does not exist. So this entire slide here has discontinuities at x equals 1 and x equals 2. And then the endpoints, all you have to do is have a filled in circle. This is continuous at both 0 and 4 because they have a filled in circle. If you have a discontinuous function, these are two examples here, where you have a hole and the function value either is absent or is different than the limit. These are what are called removable discontinuities, and you can fill these holes by a little bit of algebraic manipulation. These are called essential discontinuities, or discontinuities where you cannot remove them. And what's the purpose of removing them? The purpose of removing them is so that you can actually do some calculus on those functions. These you can't really apply calculus. Later we'll talk about derivatives, and you can't do a derivative at this spot because of the discontinuity. This is a very common function too, such as like y equals 1 over x is an example, or y equals 1 over x squared. These functions are discontinuous because of the asymptote, and they don't not able to be removed. And oscillating is really a weird one that looks like this. Doesn't come into play too often, but it might. Removing a discontinuity. There's a couple different ways to do it. The first way is to factor. So if you were in class with me today, I would probably put this one on the slide, and I'd give you a moment, and I'd say factor. Hopefully you kind of remember vaguely the SOAP method of factoring. And if you do remember, you end up factoring the top above that green line from this to this, and the bottom is just a difference of 2 squares, which factors to that. So initially, this doesn't look like it has a limit, because if you plug a 1 in there and you plug a 1 in there, you get 0 over 0, which is undefined. However, you could what's called remove the discontinuity by factoring numerator and denominator and canceling the two like factors. Once you do that, you have a simplified version, x plus 1 in the denominator, x squared plus x plus 1 in the numerator, and this will allow you algebraically, without creating a graph, to substitute 1 in for all your x's and still get a value, and you know that this has a limit, even though initially you plug the values in and it doesn't look like it has a limit. Piecewise functions also look like this. And you could also kind of mess with these to see if you do plug a 1 in here, or something really, really close to 1, like 0.99999, are you going to get an approximate same value? Is the hole filled in the same spot? Or does it kind of look like this, and like this, and then is the 3/2 higher than what the actual function might be? So these things can be removed. There's another discontinuity x equals -1 that cannot be removed, and that's when you have something like this, which is an infinite discontinuity. Composites of continuous functions are continuous, so sine x is continuous and x squared is continuous, so when you place one inside of the other, they're still continuous. Absolute value of x is continuous, cosine of x is continuous, therefore the absolute value of cosine x will be continuous. And then this is a little joke that I would do in class, and I'd say something like, hey everybody, why did the chicken cross the road? And the answer is the intermediate value theorem. So what does that mean? That means that if a function is really low here and a function is kind of higher here, or vice versa, this might be 7 and this might be 2 or something like that, then this function must hit every single value between 7 and 2. That's shorthand for IVT, which is the intermediate value theorem. That's going to be one of the most popular theorems we'll use on the AP test. Here it is, extremely important. Feel free to pause the video and write that down. That is something extremely important. Another quick example. If I tell you a function is continuous, and I'm going to put numbers here for a and b, let's say this is -2, and let's say this is 3. And at the beginning, it hits a low value of f of a, which I'll assign a number to as 1. And let's say it hits a high value at the other end point. Remember, these are the endpoints of 7. Then I know it must take on every value between 1 and 7. Does that mean it could go to -half? It can, but it doesn't have to. What it has to do is take on the beginning value of 1 and the ending value of 7 and all of the values in between. That is IVT. Here's a great question that comes from our book. It's an extremely popular AP question. It talks about continuous functions, and then it gives you like a piecewise, for example, and says that this line exists when x is less than 2. And this line, which has an unknown slope, exists when x is greater than 2. So you have to find the value of this a. It's pretty simple. You substitute 2 into the original function, and you get 4 plus 3, which is 7. So you know that this second function must also have a value of 7. If it does not, 1, 2, and the first one's a line that is less than 2, so I'm going to put a 7 right here, and it goes like this, and it's a filled-in circle, and it goes something like this. And then the other function, which is this, has an unknown slope. If it did this, let's say the slope was a little bit less than 2, so it's more horizontal, and it didn't connect, that'd be an open circle due to that, then you would not have a continuous function. So how do you get these to mesh? You need to move this guy down and make sure it meets at the same spot. So the function value must also have a 7. So if you take this and solve for a, which is the thing you don't know, what did I plug in for 2? What did I plug in for x? I plugged in a 2. You then, that was the x, and then that's the a. I just kind of flip the order there. Instead of ax, it's xa. You could solve and get a value of 3. So it must be 3, and if it's not going to meet at the same point. Extremely popular one. We'll talk about that more as we go along. That was lesson 2-3 on continuity.